Welcome to Curious Orbit. Let's jump right into this explainer. Think about this. Every single day, we seamlessly rely on our phones to tell us exactly where we are, literally down to the foot. But what happens when you leave Earth behind? I mean, imagine traveling millions of miles into the vastness of the solar system. There are no roads, absolutely no cell towers, and definitely no Wi-Fi networks to connect to. So here's the incredible mystery we're diving into today. How do you navigate the dark, empty void of deep space?
So here is the billion-dollar question that we need to answer right off the bat. How exactly does a spacecraft know its location millions of miles away? If you're trying to thread the needle and land the Perseverance rover on Mars or put a probe into a highly specific orbit around Jupiter, you can't just pull up a Maps app. How on earth do scientists and engineers achieve this mind-bending precision in an environment completely devoid of our standard navigational infrastructure?
To figure this out, we kind of have to bust a major misconception about the tech in our pockets. Your smartphone uses GPS, right? But GPS is essentially just a tiny localized bubble of satellites, actively orbiting Earth, constantly shouting out timing signals. Your phone basically just listens to them to triangulate its position. But the moment a spacecraft heads to the outer planets, it rapidly leaves that narrow little bubble. Out in the deep space void, Earth's GPS constellation is completely and totally useless. So mission controllers need a completely different method to find their spacecraft. And that method actually starts right back here on the ground. Because radio waves travel at the speed of light, space agencies across the globe use networks of massive, hyper-powerful deep space communication antennas. These giant ground stations basically act as our cosmic megaphones. They blast radio signals out into the dark toward our distant spacecraft, and then the spacecraft send a faint signal right back. But hey, just talking to a probe doesn't tell us where it is, does it? We have to turn that simple communication into a hard physical measurement. And we do that by calculating distance using travel time. It's like the ultimate cosmic stopwatch. We know that radio waves travel at the constant, mind-boggling speed of light. And space, well, space is unfathomably huge. So if a spacecraft like Voyager 1 is billions of miles away, it takes a measurable, predictable amount of time for that light-speed signal to make the round trip. If engineers know the exact fraction of a second a signal left Earth and exactly when the probe's reply came back, they can calculate the precise distance between us and the spacecraft. Okay, great. So Earth antennas give us our absolute distance. We know the spacecraft is, say, exactly 100 million miles away. But think about it. Distance alone is functionally useless if you're trying to hit a moving target. To accurately predict where that spacecraft is going to go next, we desperately need its line of sight velocity. We need to know exactly how fast it's moving. So how do we get that? The answer relies on a physical phenomenon you actually experience all the time down here on Earth, the Doppler effect. Think about the sound of a passing ambulance. As it races toward you, the siren's pitch sounds noticeably higher, but as it speeds away, the pitch instantly drops. That shifting pitch is the Doppler effect, and something literally identical happens with the radio waves transmitted between Earth and our deep space probes. Let's look at how this works in practice. When a spacecraft is speeding toward Earth, the frequency of the radio signal we receive shifts slightly higher, basically getting compressed by the forward motion. If the spacecraft is flying away, those waves stretch out and the frequency shifts lower. By measuring these incredibly tiny, microscopic shifts in the radio frequency, engineers can figure out exactly how fast the craft is traveling along that specific line of sight. So, look at what we've got. We have two massive pieces of the puzzle: distance and velocity. Problem solved, right? Well, actually, scratch that. This brings up our next massive hurdle. Space is not some flat, empty highway. Spacecraft are flying in complex, three-dimensional space, and their paths are constantly being warped and pulled. So how do we account for the immense, invisible gravitational forces scattered all throughout the solar system? This is where we enter the wild realm of orbital mechanics. A spacecraft doesn't just drive through space with a steering wheel and a gas pedal. Instead, it rides a mathematical trajectory that's almost entirely dictated by gravity. The sheer mass of the sun, the planets, even distant moons, they all exert a gravitational pull on the spacecraft 24/7. Every single tug, no matter how tiny, slightly alters the probe's path. So engineers have to build these insanely complex computer models just to predict exactly how those massive bodies will bend the spacecraft's trajectory. But models are just predictions, right? In reality, you still have to steer. Enter the Trajectory Correction Maneuver, or TCM. A TCM is essentially a highly targeted blast of a spacecraft's onboard thrusters to make tiny, precise changes to its flight path. Mission teams use those computer models to predict where the craft should be. If the radio signals tell us the craft drifted even a tiny bit, they fire the thrusters just enough to nudge its velocity and put it right back onto that perfect mathematical curve. And the stakes for getting this rate? They are astronomically high. I mean, imagine standing on a pitcher's mound and trying to throw a baseball into a strike zone that is literally millions of miles away. If the angle of your release is off by even a fraction of a single degree, that ball is going to miss the target by tens of thousands of miles by the time it reaches the plate. In space travel, a tiny navigation error early on compounds over time. So early precision is absolutely everything. Which naturally leads to another big question. If making these precise corrections is so incredibly difficult, why not take the easy way out? Why not just pack massive engines and carry tons of extra rocket fuel so we can muscle our way through space and just brute force any massive mistakes? Well, welcome to a classic physics trap known as the tyranny of the rocket equation. Here's how it goes. Step 1. Carrying extra fuel automatically increases the weight or mass of your spacecraft. Step 2. Moving a heavier mass off the Earth requires a much larger, way more expensive launch vehicle. Step 3. That larger rocket requires exponentially more fuel just to lift the extra fuel you added in step 1. It's a vicious, cascading chain reaction. We literally cannot carry infinite fuel. It's physically and financially impossible. So, engineers had to find a much cleverer way to alter velocity without burning propellant. The brilliant workaround? The gravity assist. Often called the cosmic slingshot, this maneuver uses the gravitational environment of the solar system to our advantage. Instead of hauling all the energy you need in the form of heavy liquid fuel, you purposefully fly dangerously close to a massive planet. The planet's gravity grabs the spacecraft and dramatically alters its trajectory and speed, and it does it entirely for free. This is exactly how the Cassini probe reached Saturn and how the Voyager probes managed their grand tours of the outer planets. Now, we absolutely need to keep the physics accurate here. A spacecraft doing a gravity assist isn't just magically creating energy out of nothing. No way. Instead, it's physically exchanging momentum with a massive moving planet. The spacecraft essentially steals a tiny bit of the planet's orbital momentum to boost its own speed relative to the sun. Because the planet is unfathomably huge compared to our little probe, the slowdown for the planet is entirely unnoticeable, but the spacecraft gains enough energy to go hurtling into the outer solar system. But as we all know, space is messy. Even with perfect gravity assist math, what happens when the universe throws you a curveball? We're talking about tiny, unmodeled forces that constantly mess with the trajectory. The physical pressure of solar radiation hitting the craft, microscopic bits of gas venting from the hull, thrusters that randomly underperform by 0.1%. How do you navigate when the environment is constantly trying to push you off course? You counter it with ruthless consistency, specifically the deep space navigation loop. It's a continuous procedural cycle that mission teams run over and over. First, they measure the spacecraft's distance and speed using those radio waves. Second, they predict its future path using the gravity models. Third, they compare the actual data with the prediction. Fourth, they correct the drift with a small thruster maneuver. And fifth, they repeat this exact loop for months, sometimes decades, perfectly refining the path over time. However, as spacecraft push deeper into the dark, a final massive challenge emerges. Deep space communication delays mean spacecraft cannot be controlled in real time. Remember that speed of light limitation? If a spacecraft like New Horizons is way out by Pluto, a radio signal from Earth might take over 4.5 hours just to reach it, and another 4.5 hours for the confirmation to come back. You can't just operate a joystick. Spacecraft absolutely require a sophisticated level of autonomy. This is where autonomous onboard tools like star trackers come into play. These are basically high-tech cameras that photograph the surrounding star fields. Because distant stars have extremely fixed predictable positions, the spacecraft's computer can autonomously compare its photos to an onboard star catalog. By matching the patterns, the spacecraft instantly determines its exact orientation or attitude in 3D space without ever waiting for a delayed signal from Earth. So, bringing it all together, we can see that modern deep space navigation isn't about relying on just one magical device. It's a beautifully blended symphony of engineering. We use massive Earth-based tracking tools for ranging and velocity. We rely on onboard autonomous tools like star trackers and inertial sensors to maintain orientation. And we wrap the whole shebang in complex mathematical models to predict the future. Which brings us to this incredibly profound realization. Out in the vast, empty dark of the outer solar system, there are no maps, no roads, and definitely no helpful GPS satellites pinging your phone. Instead, humans use the fundamental laws of physics themselves as a navigation system. We have literally turned the constant speed of light, the stretching of radio waves, and the massive gravitational pull of planets into the ultimate cosmic roadmap.
If you had to choose, would you trust Earth-based navigation or an autonomous spacecraft to navigate deep space? Tell us your choice in the comments and subscribe to Curious Orbit for more space science and technology.